We're not connected. Alrighty, good morning. Let's get this going. Oops. So, we're going to talk today about continuing with E2 reactions. And so, we saw last time that, remember, we need an anti-periplanar hydrogen to our leaving group. And typically, if we're going to want a Hofmann product, which is just typically what E2 reactions are used for, you want a bulky base. You can get the Zaitsev product if you use a smaller base, but often you'll get a mixture of products. So because we like to control things, usually E2 reactions are better suited for bulkier bases to force us to get that Hofmann product. So typically, remember, we want the polar aprotic solvent. We want a strong base. Generally, a bulky base is what you're looking at here, because we often are looking to use E2 reactions to get us the Hofmann product. We'll see E1 reactions are a little bit easier to get us the Zaitsev product, which is the more substituted alkene. And then we have the substrate. It needs a beta hydrogen that can be anti-periplanar to the leaving group. All right, so this was our conditions for doing an E2 reaction. So if we have something like this, if we just use a base like sodium hydroxide in acetone, oftentimes heat helps eliminations happen rather than substitutions. I'm in fact going to make this tertiary just so we don't have to worry about any substitutions happening. Remember, substitutions don't happen on tertiary leaving groups. So if we do this, we're going to get a mixture of our eliminated product, that's the Zaitsev product, and our Hofmann product. If we use triethylamine instead, we will pretty much get only the Hofmann. So this would be our major product here, and we would have the minor product as the Hofmann. Because this hydroxide is nice and small, it can go ahead and pluck protons off wherever. It's generally better to make the Zaitsev product. Zaitsev product is more stable. But if we want to, for whatever reason, if we want the Hofmann product, generally doing a bulky base will give you the Hofmann almost exclusively. So the bulkier your base is, you're only going to get Hofmann out. I don't know the exact ratio you'd get of Zaitsev to Hofmann using hydroxide. Maybe it'll be like 75-25. But that's a mixture of products. Generally, we want to avoid those. So we're going to see that we can control where we end up having this depending on what our base is. Okay, so if you want Hofmann, use a bulky base. If you want Zaitsev, E1's probably better, but E2 will work. And you'll have it as your major product, so most of it will be there, but you will lose some to the Hofmann product. Alrighty. Let's talk about alkenes. So a few notes on alkenes. The more substituted the alkene is, the better it is. So that means, what I mean by substituted, the more things we have on it that are not hydrogen, the better we are. This will be our most stable of these. And I should mention that if you just have di-substituted, trans is better. Trans is typically more stable because you can have some steric bumping with cis alkenes. So just note here that cis alkenes, di-substituted alkenes, are less stable than trans ones. So just keep that in mind. But they're still better than having just one substituent. So that's why we see the Zaitsev product is often preferred, is because it will give you the more substituted alkene that's always more stable. So that's what we're looking for with these reactions. Alrighty. If we want to talk about naming alkenes, because why not? We've learned so much about naming other groups. Let's talk about naming alkenes. Don't forget, when we talked about stereochemistry, we talked about E and Z, or Z and E. This, we have the higher priority depending on what those are relationship to each other, we have special letters to describe that. So the high priority groups, if that means by atomic number. High priority groups, if they're trans to each other, that's an E alkene for Entgegen. And then if your highest priority groups on each side are cis to each other, then it's a Zusammen, a Z alkene. But in terms of naming alkenes, this was pentane, right? This one we would say is 1-pentene. So all we do is we change the A to an E. Or we can say pent 1-ene. Either of these are acceptable. These are both good. So this will work. All right. So in this case, you list the carbon that your alkene starts on. So this is the locator number for where the alkene begins. It's understood that it ends on the next carbon, right? Because an alkene is 2 carbons. We understand that. So we name the number, or we give the locator number for where it begins. If we have something like this, with 2 alkenes, I'm going to give it so it gives the lowest numbers. If I started from the right, I would end up with 3 and 5. as my numbers, but here I can do 2 and 4 if I start from the left. So we're going to see that this would be 2, 4 heptadiene. So we have 2 alkenes in this one. So we have diene, 2 alkenes here, and we have our locator numbers. We probably, with this one, we would need to say also that these are both E alkenes. So we would say 2E, 4E, 2,4-heptadiene if we were to be really good about it. Those are, I mean, we can see very clearly those are E alkenes, right? Trans alkenes are E. So that's what we'll have there. And remember, with alkenes, you're looking at both sides. So you're looking at carbon 2, you're looking at carbon 3. Which direction are our substituents pointing? They're both away from each other. So that's going to be an E alkene. For the first one, we don't have an E or Z because we have it's terminal. It's a terminal alkene. We have 2 hydrogens on it, so it's the same thing. We don't have an E or Z for that. Same thing, by the way, if we had something like this. If we had something like this, we would have to name this 4E 2-methyl. Let's see what 2,4-heptadiene. I'm gonna write that down there. Again, you can put the 2 and 4 in the heptadi 2,4-ene. That would work too, but I'm okay if you put it at the beginning of the parent name. Notice we don't have any stereochemistry for the 2 because methyl and methyl are equivalent to each other. It's not as a, we don't say chiral for this because they're sp2 carbons, but they are they're identical. So we can't say that it's cis or trans because it's neither. It's equal. So there's no E or Z for carbon 2. All right, but we still have one for carbon 4. And of course, we can do all this fun stuff too with cyclic alkenes. This would be 1,3-cyclohexadiene. Fun. If you only have one, this would be cyclohexene. Nothing crazy there. When we're putting on alkenes, because now we have a higher priority group, the longest chain of your compound must include the highest priority group. Functional group. And right now, that is an alkene. The only thing that we have learned are alkenes. All the rest of them are lower priority than alkanes, so we just keep them as, hexane as our parent name. For now, though, we're going to see that we have to have I don't know, whatever. Here's some crazy compound. Our longest chain for this compound has to include our highest priority groups. So our longest chain for this, our parent, is 4 carbons. We don't care about the rest of this. We have to include our highest priority groups in our on our longest chain for naming purposes. So our parent name will be butadiene. And then on carbon 2, we have a 1, 2, 3, 4, 5, 6, 7. So we'll say that this is 2-heptyl 1,3-butadiene. And technically, no, none of these have stereochemistry, so we're good. So if you have an alkene, that must be part of your longest chain. If you have two alkenes, you must include both of them in your longest chain, even if it's numerically not the longest chain. Your parent must have your highest priority groups. All right, and all the other stuff goes on there. I mean, I can throw chlorines and T-butyls and isopropyls on these. It's really the same stuff. We'll do one relatively complicated one, and then we'll move on with our lives. Oh, and you know what? Here we go. Since you guys are so good at stereochemistry now. Something crazy like this. So, let's go ahead and do it. Let's see. We have to include our alkenes in our parent chain. Let's do the numbering. Let's see what we get. Remember, we don't start at carbon 9 and say, oh, that's a T-butyl group. It is a T-butyl group, but it's part of our long chain. So we can actually get 11 carbons out of this. That includes both our alkanes. If we start numbering it this way, we can do that. However, one more rule for us. The lowest locator numbers should be given to your highest priority groups. And again, right now, that's just alkenes for us. That's the only higher priority group we have. So our options are 4,8 or 3,7 for our alkenes. And so because 3,7 is lower for our alkenes, we're going to go with the blue numbers. So even though we have substituents close on the green side, we have to give our higher priority groups their special treatment. So even though we have the green numbers. So we're going to go ahead and number this with the blue numbers. All right, so on number 3, on carbon 3, we have an alkene. And that happens to be an E-alkene because our highest priority groups are opposite sides. On the left carbon, we have an ethyl group and a hydrogen. On the right carbon, we have a chlorine and then some carbon stuff. Chlorine wins on the right, ethyl wins on the left. Those two are trans to each other, so we call that an E-alkene. On carbon 4, we have a chlorine. On carbon 5, we have a fluorine. And let's check its stereochemistry. So we're going to have priority 1 is our fluorine. Priority 2 is going to be the alkene. Priority 3 will be the other carbon. So this is an R alkene. Right, 1, 2, 3, we're going to get R. Hopefully by now R and S should be no problem for you after you did 200 problems on it. 6. We have a 1, 2, 3, 4, a butyl group. Is this R or S? Our highest priority group is That's our higher priority because it's got a fluorine. Second priority is the one with the alkene. Third priority is the plain old alkane. Fourth priority, hydrogen. So this is also an R substituent. Do we see why those are the higher priorities? So fluorine, carbon with fluorine, carbon with carbons, multiple carbons, and then the third priority is just a single carbon. So that's why. Okay, so we still do atomic number for all of these, always, for deciding stereochemistry. Number 7, we have another alkene. And that is also an E alkene, because we only have 2 groups on them that are not hydrogen, they're trans to each other. And then on carbon 10, we have 2 methyl groups. So, we have it now. So, remember, alkenes become our parent name. So, this will be an undecadiene. That's our parent name. Undecadiene, 11 carbons, 2 alkenes. If we had 3 alkenes, undecatriene, undecatetraene, however many we have. So that's taking care of these things. Let's put our stuff in alphabetically. So butyl group is first. Oh, I'm sorry, we have to do all our stereochemistry, don't we? So 3E, 5R, 6R, 7E. We are going to run out of room. I'm going to move our parent name out of the way for right now. First thing is 6-butyl, 4-chloro, 5-fluoro. Don't forget the U in fluoro. 10-dimethyl. And then here we go. Then we have our parent name there. So, very fun. So 3E, 5R, 6R, 7E, 6-butyl, fluorochloro, 5-fluoro, 10-10-dimethyl, 3,7-undecadiene. Impress your friends with these crazy names. But that is this molecule. So we've done it. We gave our parent chain had both alkenes in it. We want to include as many as possible. I'm not going to give you ones that aren't part of it. It's just too much work. We had our stereochemistry for alkenes. We had our stereochemistry for our other substituents, our chiral substituents. We had RNS for those. And then we have the rest of our substituents on there in alphabetical order. Okay? So, we've done that. Awesome, awesome. And we can go from here. So that's our alkene nomenclature. All right, so it's an important bit here. So, okay, so bulky base gives us Hoffman alkenes that are less substituted, they're less stable, but that's kind of the point. So that's what we're looking for here. Alrighty, let's look at now. Let's see, do we do SN1 first or E1 first? Blah, blah, blah. Let me see. E2. Aha. Both of them, I guess. Okay, we'll start with SN1. And then we're going to talk about deciding when to use which one and kind of look more closely at all of them. So we're going to see our conditions will dictate which one will happen. And then when we're looking at the products, we have to make some choices. So we'll see. This is a fun chapter. So let's go on to SN1 reactions. Any questions on the naming for alkenes, by the way? So we have our next functional group here. So This is what's called a first order nucleophilic substitution. So it's first order because we're going to see that the only thing that matters for rate purposes is our substrate. Cool. Okay, so Terminator Goofy. I love it. So with SN1 reactions, our rate is solely determined by the concentration of our substrate, which tells us that this is only one step in the process. And we're going to see that SN1 reactions are characterized by two steps. Step 1 is the loss of a leaving group, which gives us a carbocation. And step 2 we can even use water. As our nucleophile. So it's a two-step process to substitute in on here. And then technically our third step, we need to just make this neutral. So we'll have another water molecule come along. It's just going to come on and take away that proton. And we will end up now with our product of choice, our substituted product. So in this case, we had a protonated substitute on there, so we needed to just deprotonate it to make it our final product. We don't want to leave protonated things on. So our first step is the loss of a leaving group. Our second step is the nucleophilic attack. Not attract, attack. So our nucleophile comes in and attacks the carbocation. This is the important part here. We form a carbocation. And so we're going to see that even if we take this product, put it in some water, maybe some OH minus just to help things out, we are still going to end up with the same product. Remember, carbocations are unstable. They will migrate. So if we look at the mechanism for this, first step, we lose our leaving group. It goes away. So we get rid of our bromine. So we now have a primary carbocation. Not a good thing. So what happens, remember, is carbocations will do whatever they can to stabilize themselves. So we're going to have a hydride shift happen. And we're going to then end up putting our carbocation on the tertiary carbon. And then we can have our either an OH minus or an H2O attack. Either one. Oftentimes, we'll see that we can use either one. And unlike SN2 reactions, which take place in one step, these take two steps. And as a result, we have the potential for weird stuff to happen in the middle. An SN2 reaction on this would give us the alcohol in the same place that the bromine was. The hydroxy group would be in the same place for an SN2 reaction. For SN1, we are open to carbocation rearrangements. So for SN1 and E1 reactions, I haven't talked about E1 yet, but we'll get there. These both form carbocations. And so we must always be aware that rearrangements are likely to happen. If we can get our carbocation to a better place, it will do that. If there is an adjacent spot for it to be able to go and grab a proton, grab a methyl group, whatever needs to be done, it will do it. So remember, we have hydride shifts, methyl shifts, and ring expansions. All of these are options for us when we have carbocations. So that first example there was a hydride shift, where we're going to move to a more stable place. There is a tertiary spot next door, so the hydride ends up moving over to get that carbocation onto the tertiary spot. A methyl shift might be something like this. We lose our bromide. We're going to end up moving a methyl group over. And I do want you to write on top of the arrow what's happening if you're doing a rearrangement. If it's a hydride shift, a ring expansion, or methyl shift, I do want you to write that. So as a result, we have now moved a methyl group over, and we have our carbocation now over here. So the methyl group, I'll draw it in green so we can see where it's gone. Our methyl group has moved over to a new carbon. So it's moved on to that carbon, and now we have our carbocation on a tertiary spot. So carbocations can move one carbon over if it makes them more stable. And they can do that by either moving a hydride or moving a methyl group. Remember that carbocations can also do weird stuff with rings. If we do an SN1 reaction here, or E1, just showing the carbocations. We have two options here. Probably the better one is actually going to be the to go to the tertiary position. We could do a methyl shift. I'm sorry, a hydride shift. Let's make this a little bit more strained. That's going to make it more likely to expand. So I'm going to just change this a little bit to illustrate what's going to happen here. So yes, you could do a hydride shift, or you can ring expand. I'll just do that. If you hydride shift, you end up putting your carbocation there, right? Or you can ring expand. And what that will do is, remember I like to draw the colors on the carbon so we can see what's happening. This bond is going to break and move over. We're going to end up with a 5-member ring now, more stable. And now our blue and green carbons are one bit away from each other. So we have options here. Carbocations mess with your molecules. They destroy things. I'm going to do the hydride shift in purple just so we have that. So we have two options here. We can do our ring expansion or our hydride shift, and both of them will stabilize the molecule a little bit. So the carbocation is moved to the secondary position in the ring expansion, but it is now a less strained ring, which is a good thing. With the first one, we ended up just doing a hydride shift. We've moved the carbocation to a tertiary position. Both of these are going to happen. And that's the problem with carbocations, right? Is you're going to end up with a mixture of products as a result. So all of these rearrangements can happen, so don't forget about them when you're doing these sorts of reactions. If we want to just take a look at SN1 reactions, in sort of conditions we want, typically your reactants are a protic solvent plus its conjugate base. Like, for example, water and sodium hydroxide. That would be a common set of reactants to do in SN1 reaction. You could use methanol and sodium methoxide. These would be common things. You could also just use the solvent. These reactions are sometimes called solvolysis for this reason. So you can also just use the solvent. So just put water on there, you'll end up doing this. You need the protic solvent here, because if you don't have a protic solvent, it's not enough to stabilize your carbocations. So you really need protic solvents here, because those are going to have nice, generally oxygens or electronegative atoms that will be slightly negatively charged that are going to help stabilize your carbocation. So these are going to be protic solvents. All right, and typically that's also because we're going to use our solvent as our nucleophile. Like the first time I use water as my nucleophile. And then the second time I use hydroxide. But typically you'll have water there anyway. So that's what we're looking at here. So protic solvent and its conjugate base, or just solvent. These are the typical nucleophiles for SN1 reactions. Okay, because you really need that solvent to stabilize this. The substrate can be anything, but ideally a tertiary you'd want your leaving group on a tertiary position already. That would make it